This is about the year 1970. Physicist Stephen Hawking was searching for the answer to a very simple question. Do black holes have a temperature? Believe it or not, this single question changed some of the fundamental ideas about our universe. The belief was that this universe is infinite and eternal. There will be no end to it. But the search for this question took Stephen Hawking into a completely different world. From there, we got more information about the working of black holes. And this conclusion came forward that black holes also radiate energy, which means that even black holes, which absorb everything into themselves, will slowly lose energy. And a time will come when all the black holes in this universe will eventually... But wait, how can black holes radiate energy? Because what we all know about black holes is that their gravitational field is so strong that nothing, not even light, can escape from them. We also call them relativistic jets, the first famous picture of the M87 supermassive black hole, in which these energetic jets are clearly visible to us. So how are all these things coming out of black holes after all? Anyway, some of the mysteries and doubts about black holes will be cleared up. So let's talk about black holes first, because the root of all the confusion is hidden right here. So simply, if we try to visualize what a black hole actually is, let's start by assuming this: that if space is empty, if there is nothing in space, then the fabric of space will be completely flat. If we place a massive object in space, then a curvature will appear in space. The greater the mass of the object, the more the curvature. If the curvature is less, then the object's mass is less, and if there is no curvature at all, then the object is also massless. Now we have understood the concept of space, its curvature and mass. You can understand it in real life like a crater or a big pit. Suppose you are standing at the edge of a pit, and by chance, if your foot slips, you will roll towards the center of that pit. This pull in space-time is called gravity. The greater the curvature, the stronger the intensity of gravity will be. Now suppose you have rolled to the very center of the pit, which means you are at the center of the curvature. That means you have landed on a massive body. But now, if you want to get out of that pit, that is, if you want to escape from a massive body, to get out of its massive gravity, you will need to use a specific amount of energy. And that energy is what we call escape energy, escape velocity, or escape speed. Once you understand this, you can imagine a black hole much better. Now suppose you put so much mass in one place in space that the curvature it creates in space, or the pit it forms, is so deep that even the fastest object in the universe, that is, light, cannot escape from it. That means even light doesn't have enough energy to get out of that curvature. Now we all know that the speed of light is the ultimate cosmic speed limit. That means any particle that has mass cannot achieve this speed, and particles that are massless can only go up to the speed of light. This means that nothing can escape from the curvature created in space. So understand that a black hole has formed there, whose escape velocity is much greater than the speed of light, but even a black hole has its own limit. Let's understand this with our pit analogy as well. As long as you are far from that pit, you are completely safe. But as soon as you enter a critical region where you slip and start falling into that pit, you just keep falling. That's called the event horizon. If you fall into this region even once, then no matter what you do, you'll just keep falling into the black hole, and eventually you'll stop at the singularity. Singularity is a point where all the mass of the black hole is concentrated. If you want to know more about this, you can watch our video. You'll find the link in the I button above and in the description box below. Any objects outside the event horizon can either escape escape the gravity of the black hole or fall into the black hole. That depends on their properties. Now, from here, we know that any object that crosses the event horizon can never come back. So then, how does matter and radiation get released from a black hole? So for this, imagine yourself as a particle that's just outside the black hole's event horizon. Obviously, because if you're near the black hole, its gravity will place you in an elliptical orbit. The closer you get to the black hole, the more your speed will increase. As long as you don't cross the event horizon, you won't fall into the black hole. Now, along with you, many particles are also orbiting the black hole just like you, and you would be interacting with them. The disk formed in the orbit of the black hole is called the accretion disk. The scene of the accretion disk is such that particles are colliding with each other there. Because of friction, the entire disk heats up, and due to this heat, radiation is emitted from that accretion disk. This radiation is called thermal radiation, so actually the radiation is not coming from inside the black hole, but from the matter outside the event horizon. So, one confusion is cleared up here. However, some of the matter in the accretion disk continues to lose energy and eventually falls into the event horizon, causing that matter to reach the singularity. And the mass of the black hole increases. Besides this, a lot of other things are happening around the black hole as well. Many charged particles in the accretion disk are traveling at the speed of light, and due to their dynamics, a magnetic field is created around the black hole. This then accelerates the ionized particles in a special helix shape, and this acceleration happens at the speed of light. And this is what we call relativistic jets. They are very bright and can be seen from very far away in space. There is a galaxy called Centaurus A, from whose central black hole these jets are coming out in both directions, while in M87 it has been seen coming out in a single direction. But the important thing to understand here is that these jets and all the energy stored in them do not come from the black hole itself, but rather from the ionized particles orbiting in the accretion disk around it. Even there, nothing is coming out of the black hole, nor can anything come out. The gravity of the black hole accelerates the particles present in the accretion disk outside the event horizon, where the particles get heated up due to friction and collisions. They become ionized, which generates electric current and magnetic fields in them, and then this magnetic field accelerates these particles in one direction. This is the basic idea behind relativistic jets. Now let's talk about the most complicated Hawking radiation. It's a bit complicated, but we'll try to understand it in a simple way. So first of all, as we discussed at the beginning, if we remove everything from the fabric of space, even the black hole, that space will become a flat vacuum surface. Now we all know that mass curves the fabric of space, so if we place a black hole at a point, the space there will obviously become curved. An event horizon will form, and the space around it will be governed by the fundamental laws of the universe. Now, the result of this will be that radiation will start emitting from a large region around the black hole, which will be black body radiation, and it will be emitted in all directions. This radiation is what we call Hawking radiation. So now where is this radiation coming from? Because we've assumed that there's nothing in space except the black hole. So obviously that radiation should be coming from inside the black hole itself, because here there's nothing even outside the event horizon. Whatever energy is released in that radiation, it should come from the mass of the black hole itself. But here, our common sense tells us that nothing can come out of a black hole. So how can Hawking radiation come out, and how can it be proven? If we look at Einstein's famous equation, E equals mass times the speed of light squared, here we can say that with each quantum of energy or packet of energy of Hawking radiation, E amount of energy is coming out, so the black hole will lose m amount of mass. But how will this happen? What will be the mechanism of this whole process? Let's find out. The very first and most common simple explanation was not given by Hawking, but it couldn't really satisfy the scientists, but it gave us a new way to visualize energy. So this explanation goes something like this. When space is empty, the energy present in it is called zero-point energy, which has a non-zero positive value. Now, even though space is empty, meaning it's vacant, from the perspective of energy, we can't treat it as empty. We need something there that can occupy that energy or neutralize it, because the energy present in space is obviously already positive. And when you combine this fact with the Heisenberg uncertainty principle, a concept emerges in front of you. What happens is that in that empty space, pairs of matter and antimatter keep coming into existence continuously. They exist for a very short time and then annihilate each other, making the space empty again. This process keeps happening everywhere in space on a massive scale. Now, you can assume that the same process is happening at the event horizon of a black hole. Suddenly, two particles emerge from empty space. One is matter and the other is antimatter. Think of it as one being a particle and the other an antiparticle. If one has positive energy, the other has negative energy. Now, one member escapes the event horizon, the one with positive energy, while the other particle, which carries negative energy, falls into the black hole. This will decrease the mass of the black hole. So this explanation was suggested by Hawking, but it was for virtual particles which we cannot physically observe. And in Hawking radiation, photons are released, so was it not correct to conceptualize it with matter and antimatter particles? And most importantly, as we mentioned earlier in the case of Hawking radiation, it is released not from the event horizon of the black hole, but from a larger area around it. But if you still want to go with this explanation, then here you have to think about 4 different conditions. Because there is no guarantee that the positive particle will always escape the event horizon and the negative particle will always go inside the black hole, so here these 4 possible cases can arise, in which neither of the particles will cross the black hole's event horizon and they will annihilate each other and disappear. Number 2. Out in pairs. In this, the particle escapes the event horizon and the antiparticle goes inside the black hole. In in-out pairs, the particle falls into the black hole and the antiparticle escapes the event horizon. And number 4. In pairs. In this, both particles go inside the event horizon. Out of these 4 scenarios, there are only 2 conditions where a photon can be released, and that is through the interaction of in-out and out-in pairs. Now, the energy that is released from those particles in the form of photons has to come from somewhere. Now, it's not like a particle just came into existence from nothing and released energy, and that energy directly. It can't come from inside the black hole, because our understanding says that nothing can come out from inside a black hole. But there was a concept we saw at the beginning of the video, and that was that curvature and mass are directly connected to each other, and it's the curvature that links the black hole to the outside physical world. So this is the concept that's going to help us in this problem here. So that missing energy will come from the curvature of space, and as soon as the curvature decreases, because some amount of energy has already left from it, in the same way, the mass of the central black hole will decrease, and in this very slow process, the entire black hole will eventually disappear. So this was Hawking's explanation, but even here, the radiation didn't come out from inside the black hole, rather it was released from the particle being formed outside the event horizon, and in exchange, the energy that was lost came from the curvature of space-time, and that reduced the mass of the black hole. However, not everyone liked this explanation because no one knows how the space-time fabric works at the quantum level in highly curved regions, especially near a black hole. But quantum field theory does have some answers to this. Quantum field theory calculations in space have given us some very surprising results. The thermal and blackbody radiation emitted from a black hole's event horizon depends on the size of the event horizon. For example, the smaller the event horizon, the greater the curvature of space there, and the greater the curvature, the higher the rate of Hawking radiation. That means the rate of Hawking radiation does not always remain the same. For example, if there is a very large black hole, as time passes, its mass will decrease due to Hawking radiation and it will become smaller. As the black hole shrinks, its mass will decrease, and this process will become even slower, and eventually the black hole will evaporate. A black hole with the mass of our sun would take 10 to the power of 67 years to evaporate. It would take 10 to the power of 87 years for the central black hole of the Milky Way to evaporate, and for the largest black hole in the universe, 10 to the power of, it will take 10 to the power of 103 years to evaporate, and by then every star in this universe will have died. Particles will move infinitely far away from each other. That means our entire universe will have died by then, and this whole universe will have lost its ability to create complex structures. Now, the last remaining energy will only be left in these black holes. When the black holes are in their final stage, there will be a cosmic burst from one of these, which will be just like a Big Bang, and then something will finally come out from inside the black hole. The light that is trapped inside it today will then try to illuminate this universe, which has turned into a graveyard. This is our galaxy way. It is just a part of our universe. Our galaxy is neither smaller nor larger than the other galaxies seen in this. Ours is so unique that there are galaxies here that are millions and billions of times bigger than the Milky Way. And at the center of all these is what drives these giant galaxies. A supermassive black hole, the master of darkness, which is one of the greatest mysteries of this endless universe. As far as we have come to know black holes, they have always been a center of attraction for all of us. The most mysterious and so vast that there is no need to even describe their power. These cosmic giants, often described as terrifying, remain hidden at the centers of galaxies. These unimaginably powerful giants have been visible to us in the history of the universe since the very beginning of its existence. Scientists have recently found evidence suggesting that black holes existed in our early universe much earlier than we previously thought. This discovery could change our understanding of the early universe. After all, what were these mysterious objects doing at the very beginning of the universe? How did they form so quickly, and how did their evolution happen in that early universe? Astronomers have been puzzled for a long time about the presence of quasars in the early universe. The discovery of quasars in the early universe means that supermassive black holes existed there, and this conclusion has left scientists even more astonished. These observations have raised many questions. How could supermassive black holes have formed in the early universe, which was not even a billion years old yet? When they didn't even have enough time to grow and evolve. So were they born as unusually massive giants, or did they somehow learn to grow very quickly by breaking the rules of the universe? A study has been published in the Astrophysical Journal Letters using data from the Hubble Space Telescope. And this study revealed that the early black holes were less luminous and were growing in a universe filled with darkness. Because of this characteristic, they had managed to escape our observation until now. This astonishing discovery not only deepens this mystery even further, but it also provides us with a lot of new information about the formation of black holes. Let's go on a journey of black holes today and see how these black holes were forming in the early universe. We'll also take a look at what the James Webb Space Telescope has told us about black holes. So get ready to embark on an exciting journey filled with the mysteries of this universe. The mystery of early supermassive black holes is one of the biggest unsolved puzzles in science so far. How did supermassive black holes come into existence right after the Big Bang? Quasars, which are some of the brightest objects in this universe, are powered by giant black holes. Scientists observed these quasars in galaxies present in the early universe when the age of the universe was not even 1 billion years. Now these objects are such that in just just 1 billion years, they grow so much that they become supermassive black holes and form quasars. It's just not possible. It's like if I ask you, have you ever seen a 10-year-old old man? You'd say, how can someone be born and become old in just 10 years? Same? Even scientists are puzzled after seeing this case. If they had so little time, then how did they grow up so quickly? When it comes to black holes, they grow by swallowing the gas, dust, and other things around them. All this matter falls into the area of the black hole's accretion disk, and from there, it slowly gets absorbed into the black hole. As this matter falls into the black hole, it collides with the other matter present in the accretion disk. Because of this, due to friction, it heats up, and that's why all the matter present in the accretion disk reaches a very high temperature, which causes intense radiation to be released from the entire accretion disk. This radiation creates a pressure barrier and puts a limit on the black hole's matter consumption, which directly affects the growth of the black hole. Considering this limit, Galactic is unable to explain how, despite this limit, black holes became so massive in such a short time back then. The two possible solutions given by scientists are either these giant black holes were formed from stellar mass black holes, which are the remnants of a massive star that dies very quickly, so it takes them less time to reach the stage of a supermassive black hole. But if this process speeds up a little, then they can grow within a given limited time. Now, because they start off with a mass 1,000 times heavier than our sun, that's why they're also called heavy seeds, and because of this, they quickly reach a large size. But where did these heavy seeds actually come from? One theory suggests dark matter halos. This is a structure made of invisible matter that holds galaxies together. This structure is very large. They even trap gas clouds in large quantities and prevent those clouds from turning into a star. When stars do not form from those gas clouds, they collapse directly into a black hole, which leads to the formation of a large heavy seed. However, the problem still remains. Only a few dark matter halos have been found to be large enough to trigger the direct black hole collapse. Black holes formed in this way should be found in very small numbers in the early universe because the dark matter halos that create them were themselves quite rare. But a recent new research shows that the number of black holes we have observed in the early universe is much higher than our calculations. And because of this, astronomers are now forced to believe that some very mysterious forces were at work in the early universe, because of which our current science is unable to understand them. Now, how can it be that there are black holes and there is no mystery associated with them? Because of advanced technology and discoveries like gravitational waves, astronomers are now able to find black holes hidden in galaxies that existed in the early universe. Earlier, we could only detect those bright quasars because they are very bright. But recently, observations from the Hubble Space Telescope have also discovered many faint black holes, which had been hidden from us until now. Scientists monitored 15 years of brightness data from galaxies, which has enabled them to estimate the black holes that are quietly growing in the universe. This method has given us new data, which shows that the number of black holes we previously assumed to exist, actually in the early universe, their number is many times higher. The James Webb Space Telescope has taken this discovery even further. Thanks to its extraordinary sensitivity and advanced spectroscopic capabilities, the James Webb Space Telescope has also started detecting faint black holes in the early universe. It is closely monitoring their activities. This telescope is also capable of detecting the faint glow of black holes hidden within galaxies. This will help astronomers refine our early models of the cosmos. But then, this raises another question. If so many black holes existed at that time, how did they all grow so quickly? After all, where did so much matter come from for them to consume? According to scientists, the answer to this might be hidden. In mealtime variability, unlike stars, black holes do not grow continuously in their eating habits at different times. Instead, they keep a gap in their eating times. They take breaks, which makes it difficult to estimate the actual rate at which their size increases. Black holes deceive us here as well. This discovery is also groundbreaking because it contradicts our previous models, meaning it proves the models we created to be wrong. Scientists now believe that all the black holes discovered so far, from extremely bright quasars to the recently discovered dimmer black holes, there are too many of them to have all formed through direct collapse. This suggests that there must have been some extremely mysterious processes at work during that time, which were not only creating large but also a huge number of these black holes. In the next 5 years, the James Webb Space Telescope is going to play an important role in solving this cosmic puzzle. Its ability to see faint black holes also gives scientists the power to observe the death of the earliest stars. And this event can tell us where the initial seeds of black holes came from in such large quantities and how the universe continued its journey forward. Scientists can also observe the death of the earliest stars and understand how the journey of the stars came to an end. Just like a normal star forms, but when dark matter is present in that normal star formation, something mysterious happens. As soon as the gas present in the cloud contracts, that is, shrinks. It captures dark matter particles in large amounts, and these particles modify the internal structure of the normal star that is about to form in such a way that the process of nuclear fusion at its core stops, which is what makes stars shine. Without the fusion process, this star cannot shine like a normal star, but it lives much longer than those stars and becomes extremely massive. And eventually, these stars collapse under their own weight and turn into a black hole, which is much larger than any normal stellar mass black hole. It's fascinating to think that if these objects existed in our early universe, observing the collapse of those first stars with our telescope. It could tell us whether dark stars played a significant role in black hole formation in the early universe or not. This adds another exciting possibility to the growing list of questions about these black holes. Are there some processes at work in the universe that we haven't fully understood yet? The future of black hole research holds a great possibility for such fascinating discoveries. In the past few years, there has been a new revolution in research in this field. Upcoming missions like the Euclid mission and the Nancy Grace Roman Space Telescope will help not only in observing faint black holes but also faint quasars. Meanwhile, observatories like the Square Kilometre Array or Square Kilometre Array being built in Australia and South Africa will help us understand black holes in greater depth. But for now, James Webb Space Telescope is leading this research. It is helping refine our old models by observing some of the faintest black holes in the early universe. In the coming years, with its help, we will even be able to find a star collapsing, and that discovery will be historic. We are trying to learn and understand our own history, but maybe that's just how the universe is. Those who predicted the end of time and Earth gave an exact date when the great destruction will come, when everything will be swallowed by time. These prophets or enlightened individuals do not belong to any single religion or culture, but have appeared throughout the world in different eras and different environments. Whether it is the great European philosopher Nostradamus or Baba Vanga, who delivered messages about the future from the ancient land of Macedonia, we humans have always been eager to know and predict our future. Whether it was the date of December 21, 2012 or the warning of doomsday on April 23, 2018, these all, every year, called prognosticators always mention some date on which human civilization or the entire planet Earth is supposed to be destroyed in some catastrophe. But these dates come and go and nothing ever happens. In such cases, these things just seem like smooth, empty talk with no real foundation. People associated with astrology have their own beliefs about this. Even scientists were scared by the discovery of this black hole. What National Aeronautics and Space Administration discovered inside a black hole will shock you. People associated with astrology have their own beliefs about this. No matter how terrifying they are, no matter how massive the destruction they bring may be, but their role in maintaining the balance of this infinite universe cannot be denied. Black holes are an ultimate truth of this universe which no one can deny. Before 2019, it was just the name of a mathematical abstraction appearing in astrophysical theory. But today, these are accepted celestial objects. Their number in this universe could range from hundreds of thousands to millions. Recently, scientists observed some strange activities in a galaxy which indicate a terrifying collision between two black holes there. The galaxy named SRSSJ 1430 plus 2303 is located about 1.1 billion light years away from us. The time it takes for the collision event is quite short. However, in a real-life scenario, it will take a considerable amount of time for this event to actually happen. Scientists have suggested that these black holes will take about 3 years to completely collide and merge into each other. If we view this as a research opportunity rather than focusing on the terror of destruction, it could be a landmark in astrophysics history. Here, we humans will witness an event that is not only super rare, but also something that very few ever get to see. But there is a problem here, and that is, even now, scientists are not 100% sure about this. What we're imagining will actually happen in galaxy SRSJ 1430 plus 2303. By the way, there is a little confusion about this, but our understanding so far tells us that we are moving in the right direction. A few years ago, in 2015, scientists observed some small black holes in space that were extremely close to colliding with each other. During the observation of these black holes, a very astonishing pattern of cosmic catastrophe emerged before us. Because of this, scientists learned a lot about the behavioral changes of these massive bodies present in the space fabric and the action of gravitational waves. A dedicated gravitational waves option has also been developed to study the gravitational disturbances and waves generated by black holes, where the most modern and advanced gravitational wave detection instrument is currently available. Of course, for an ordinary person, witnessing these catastrophic events happening in space would be a terrifying experience. For researchers making these observations, it's simply part of their job. For these detectors, witnessing any massive black hole collision or impact explosion is an absolute treat, because after that, they get all the information related to that event, which proves to be very helpful in enriching their scientific database. If, for a moment, all our observational instruments fail to detect those waves that have been generated due to these collisions, then, in that situation, many facts are excluded from the visual study. As I said earlier, light has an amazing significance in space, especially from a research perspective. Light is very important, because whenever such massive events occur, a huge explosion is created which releases a big burst of light, and this very light, when we capture it in our telescopes and read its data and analyze it, we find out exactly what is happening there. Through the photometrical investigation of the entire event, we learn fascinating things about the collision impact and the physics of both those objects. For example, when these phenomena were deeply investigated, it was found that the event of black holes merging doesn't just bring destruction, but also gives birth to a marvelous cosmic object. Obviously, after the merger of two black holes, a black hole is formed, but it is many times larger and more destructive than before. I am sure you must be familiar with the concept of galactic merger, and even if you aren't, let me quickly tell you that in this universe, one galaxy also interacts with another galaxy, and when they come face to face in their paths, they merge together. Galactic collision is one of the most dramatic events in this universe. In fact, this is actually the event that prompts two massive supermassive black holes to collide with each other. Well, you all probably know that usually there is only one supermassive black hole at the center of a galaxy, and most of the galaxy's elements revolve around it. In such a case, when a merger happens between galaxies, eventually the black holes of both galaxies also come face to face with each other. In this situation, the weaker black hole surrenders to the stronger one and becomes a part of it forever. Astronomers call this event a binary merger. To detect this, scientists study the fluctuations of light in a particular galactic cluster where objects are coming closer in declining orbits. It gives a clear picture of black holes. The galactic nucleus, that is the center point of the galaxy, is perhaps one of the strangest things in this universe. It's quite difficult to understand what we get from here. Also, the center of each distinct galaxy tells a completely different story, and to understand it, we have to choose a new approach every time. Especially the scientists present in China, and they have been quite successful in their endeavor. They tried to understand this gigantic black hole. About 200 days of wave observation data from different observatories around the world was collected. When the data was analyzed collectively, they found that there was a change in the light coming from the center of this galaxy. And this was only possible if two giant monsters were merging here. This fluctuation in light was only on a major scale, which essentially rules out the presence of any other factor. And this proved that we have indeed witnessed the biggest black hole collision so far. As far as the space catastrophe is concerned, black holes could definitely be a reason for the destruction of our beloved solar system. In reality, they are so powerful that they have the strength to swallow entire galaxies. In that case, a small system like the solar system is nothing in front of a black hole, so that's a different issue altogether. If you're also interested in knowing what would happen if a black hole comes straight at us and tries to swallow our Earth, that scene would really be worth watching. If you want to experience that feeling too, go down to the comments and make a request. Soon, a detailed documentary on that will be coming for you as well.